Particle swarm optimization is a population-based algorithm inspired by social behavior to find optimal solutions. Think of birds flocking or fish schooling cooperating to locate a target in space. Each particle represents a candidate solution with a position, a velocity, and a personal best record. Particles share information to collectively move toward regions of higher fitness or lower cost. PSO is simple to implement, has few parameters, and works well on many continuous problems. We will now visualize particles exploring a fitness landscape and step through the math and code. Here is the fitness surface, a continuous topography where peaks represent high fitness values. Particles are initialized randomly across the landscape, exploring different regions simultaneously. Each particle evaluates its fitness and records its personal best position when it finds improvement. Particles communicate the best found position so far, and the swarm adjusts direction accordingly. Over iterations, particles converge toward promising peaks, narrowing their search area around optima. We also visualize exploration versus exploitation as particles maintain diversity or focus tightly around a solution. The core velocity update is v equals w times v plus c1, r1 times p best minus x plus c2, r2 times g best minus x. Here w is inertia, c1 is the cognitive coefficient, c2 the social coefficient, and r1, r2 are random scalars. The position update is simple. X equals x plus v, moving each particle according to its velocity. Let's step through one numeric update. Compute r values, apply coefficients, update v, then x for a single particle. As iterations progress, velocities typically decrease and the swarm tightens, indicating convergence toward optima. Parameter strategies like reducing inertia or using a constriction factor help balance exploration and convergence. A compact Python core loop looks like: for each particle, compute v equals w times v plus c1 rand times p best minus x plus c2 rand times g best minus x, then x equals x plus v. In Python, you typically maintain arrays for positions, velocities, and p best, then update them in a loop with random factors. Practical use cases include engineering design, optimization, hyperparameter tuning, and mobile robot path planning. Compared to gradient methods, PSO requires no derivatives and can escape local minima, but may need many evaluations. Quick tips: select sensible coefficients, monitor diversity, and use boundary handling or velocity clamping to maintain stability. In summary, particle swarm marries simple rules with collective intelligence for robust optimization. This simplicity enables efficient implementation, scalability to high-dimensional problems, and adaptability across a wide range of engineering and data-driven applications.